Hello everybody, we are the Texas A&M Senior Design Brittle Fracture team sponsored by INEOS. The objective of this project was to analyze the susceptibility to brittle fracture in a carbon steel pressure vessel and to design a solution to prevent brittle fracture conditions from occurring. On the right, you can see the initial schematic provided by INEOS to the team. The pressure vessel outlined in red, DD308, is the pressure vessel experiencing brittle fracture conditions. This is a result of pressure control failures, which lead to a rapid drop in pressure. This drop in pressure causes the liquid ethylene to evaporate, drawing heat away from the pressure vessel, thus resulting in a rapid decrease in temperature. This process is known as auto-refrigeration, which can eventually lead to brittle fracture. Brittle fracture is considered a catastrophic failure mode as it occurs rapidly without warning. The diagram on the right indicates the three required conditions for brittle fracture: crack or notch present, sufficient applied stress, and susceptible steel as a result of cold temperatures. In order for the team's solution to be effective, it needed to ensure that one of these conditions was not met. In the spring semester, a brittle fracture assessment at DD308 was conducted via industry codes ASME B31.3 and API 579. Both the shell and the head of the pressure vessel were tested, as these were the weakest components. The gray line is the MAT, minimum allowable temperature, uncorroded, and the orange line is the MAT, corroded. The blue line is CET, the critical exposure temperature. At any given pressure, the MAT must always be colder than the CET. As can be seen, from roughly 150 psi to 100 psi, the MAT is warmer than the CET. Thus, the pressure vessel failed the assessment and the team moved forward with designing a solution. The team's design solution consists of the installation of a secondary pressure vessel connected to DD308 via a pressure sustaining valve. This pressure sustaining valve will maintain pressure in DD308 automatically and ensure that auto-refrigeration cannot occur. In order to validate the effectiveness of the pressure sustaining valve, finite element analysis of the stresses experienced by DD308 was conducted. In addition, computational fluid dynamics in combination with industry codes were applied to the system in order to verify the operating conditions. In addition to the design solution just discussed, the team conducted Sharpie V-notch experimentation to determine if replacing pressure vessel DD308 with a different metal would prevent brittle fracture. Sharpie V-notch testing consists of dropping a hammer onto metal samples and measuring the impact energy. By testing at varying temperatures, a brittle to ductile transition curve for a metal can be developed. The goal was to find a metal with a ductile to brittle transition temperature colder than the current pressure vessel. The team tested 3 different metals, each at 2 different heat treatments. The current material pressure vessel DD308 is A516 carbon steel normalized. Temperatures varying from -10 degrees Celsius to -60 degrees Celsius were tested. The ductile to brittle transition curves for each metal and heat treatment combination can be seen. The stainless steels 304 and 316 had higher impact energies than carbon steel. However, they are also much more expensive and not necessary for the applications INEOS was looking for. As a result, the team decided to move forward with the A516 carbon steel annealed. This is a comparison of A516 annealed and A516 normalized. As can be seen, A516 annealed has a ductile to brittle transition temperature 10 degrees colder than that of A516 normalized. This was enough of a difference for the pressure vessel to then pass the brittle fracture analysis that was shown earlier. Thank you for listening.